Hello everyone. So today we are going to discuss about traveling wave tube. So we will discuss in this introduction of traveling wave tube, then slow wave structure, helix traveling wave tube, how it works, and specification and application of traveling wave tube. In the previous lectures we discussed about klystron. So we will also discuss about the comparison between klystron and traveling wave tube. So, introduction is traveling wave tube is a non-resonant structure, and generally two type of traveling wave tubes are used. First one is helix traveling wave tube, and second one is coupled cavity traveling wave tube. Helix traveling wave tube use slow wave structures and used for broadband applications, while coupled cavity traveling wave tube used for high power applications. So before going to the helix traveling wave, let's first talk about slow wave structures. Slow wave structures are used to slow down the electromagnetic wave. Now the question is why we need to slow down the electromagnetic wave. The answer is the phase velocity of electromagnetic wave is greater than the velocity of light in a ordinary waveguide, and the electron beam can be accelerated up to a fraction of velocity of light in vacuum. So there is a huge mismatch in the velocity of these two. One is electromagnetic wave and another is electron beam. Means in case the electromagnet in speed or velocity of electromagnetic wave and electron beam, there is a mismatch of velocities. So because of this velocity mismatch, there will not get enough time to interact with each other. So there will be no energy transfer from one to another. And to increase energy transfer, we need to decrease the velocity of electromagnetic wave, so that electromagnetic wave can get enough time to interact with the electromagnetic wave, and this job is done by slow wave structure. And as the operating frequency increase, both the inductance and capacitance of resonant, because both inductance and capacitance inversely related to frequency. So by increasing frequency, inductance and capacitance should be values should be decreased in order to maintain resonance at operating frequency. In at resonant frequency, both gain and bandwidth product should be constant. So if bandwidth is high, so gain should be low. So several non-resonant periodic circuits or low-wave structures are designed for producing large gain over a wide bandwidth. Okay, these are some slow-wave structure that generally used. First one is helical line, then folded back line, zigzag line, interdigital line, and corrugated waveguide. What happened in these structures is electromagnetic wave travel through these guides or these lines, so it takes more time, or we can say the velocity of the electromagnetic wave reduces inside these lines or waveguides. So we can match this, the velocity of electromagnetic wave with the velocity of electron beam. The most commonly used structure is helical coil with a concentric conducting cylinder. Okay, this is a helical coil. Suppose this distance is d, and this is P. So by Pythagoras theorem we can calculate this distance, which is under root of P square plus pi d square. Okay, if we have to calculate the ratio of velocity of along the pitch and phase velocity along the coil, then as velocity is displacement upon time, it is taking the same time, so velocity ratio of these velocity is the distance, that is Vp upon c is equal to P upon under root of P square minus pi d square, that is sine of psi. So if we divide by P in this, so it and taking C this side, Vp is equal to C upon 1 plus under root pi d upon P whole square. From this equation we can see that the value of phase velocity is decreased, and by varying the values of d and p we can vary the phase velocity. Here c is the velocity of light, which is 3 into 10 to power 8 meter per second. P is, this is helix pitch, and this is diameter of the helix, and xi is pitch angle. Okay, so if we come to helix traveling wave tube, Kompner in 1944 invented this helix traveling wave tube. In case of TWT, the microwave circuit is non-resonant and wave propagate with the same speed as the electron in the beam. This is the circuit of helix traveling wave tube. So generally it consists a electron gun, which is used to inject electron in the tube, and here we can see an RF input and RF output signal. At input side, the RF signal is given to this TWT and it is taken out from the output side. A surrounding magnetic field to hold the electron beam as they tend to spread out because of the repulsive force present between the electron, and that magnetic field is produced by that permanent magnet present, that is that permanent magnet present surrounding the helix. Okay, next thing that here is used is edge attenuator. What is the use of attenuator? It is used to attenuate any reflected wave generated due to the impedance mismatching, and this attenuator is placed after a sufficient length of RF interaction region, so that the attenuation of amplified RF signal is insignificant as compared to the amplification. And the last is collector. This is used to collect the electron beam. Now some specifications are: frequency range of this TWT is 1 to 100 gigahertz. Output power, average output power is up to 10 kilowatt, and power gain is 60 dB. Efficiency is 20 to 40%. Now come to some applications of traveling wave tube. It is used for low noise radio frequency amplifiers in broadband microwave receivers, repeater amplifier in wide band communication link and long distance telephony. And due to long tube life, TWT is power output tube in communication satellite. Another use is for medical power and high power satellite transponder output, and can be used for continuous wave high powered traveling wave tubes. They can be used in troposcatter links, and they can be used in airborne and shipborne pulse high power radars, and they can be used in ECMs, that is electronic countermeasure system. Also they can be used in